Good afternoon, everyone, and welcome to MOS Live Ask a Scientist. In just a few moments, we are going to be meeting our educators who will be answering all of your questions about lightning. My name is Christina. I go by the pronoun she, her, hers, and I'll be serving as your moderator today. And if you would like to share a question today, you can do so by clicking on the Q&A button at the bottom of your screen. If you need to use captions today, you can also get those by selecting Show Captions at the bottom of your screen on Zoom. If you happen to be watching today on Facebook or YouTube, unfortunately, we will not be able to see your questions, but we're so happy that you're here joining us. And don't forget to include your name and age if you would like a shout out today. Now, all that being said, I would like to invite our educators to turn on their cameras, introduce themselves, and they're going to be sharing their favorite fact today about electricity.
Excellent. Thanks, Christina. Hi, everybody. My name is Karen. I think one of my favorite things about electricity is, in fact, a really amazing lightning storm. We're kind of getting out of the season of really good lightning storms, but hopefully we'll get one more whopper before we turn into true fall and winter.
Hi, everybody. My name is Matt. My pronouns are he, him. And I think my favorite thing about electricity is that it can be responsible for the massive blasts in the clouds that we call lightning. But the same phenomena is also what makes your heart beat and your brain think and your muscles contract.
And hi, everyone. My name is Megan. I use the pronoun she, hers. And my favorite thing about electricity is that there's actually animals that can produce their own electricity, like electric eels. And there's animals that can detect electric fields really well, like sharks or even bees can detect electric eels. Can detect electric fields. So that's my favorite thing.
Awesome. Those are all really fun facts. So thank you for sharing, everyone. And to get us started today, I think we'll just start with the basic question for you all to answer, which is talking a little bit about electric charge, since I think that'll set us up well for understanding anything else we talk about today.
Sure. So I can answer a bit about that. What we call charges is a looser word for the tiny particles that make up atoms. And atoms are the particles that make up all matter in the universe. Positive charges are the protons that make up the middle of an atom, along with a different kind of particle called a neutron that we're not going to deal with here because they don't have any charge. But the protons are positively charged, whereas the negative charges are a different kind of thing called an electron that in the old days used to be thought of as a particle that went around the nucleus. Now we tend to think of them as more of clouds of energy. So basically, those are the two types of charge.
That's a great foundation. Thank you, Matt. And just to clarify from Megan, I think you mentioned with the eels something about an electric field. Would you be able to clarify what an electric field is?
Yeah, so kind of putting it in context of the animals that I was talking about being able to really sense that electric field is that they're sensing all the little currents of electric charges that are sort of passing through the air. We as humans and all animals really do give off our own very small electric field. So those little currents are moving away. And some animals are just really excellent at detecting those small electric fields. And it also seems to be particularly marine animals, so animals that live in the water.
Excellent. Thank you for clarifying. And we have a question from Elizabeth, age 8, who would like to know, what is lightning? Excuse me, what's lightning? How does it work? And how is it made? So it's really a three-parter.
Those are all great questions, Elizabeth. I'll take that one, or at least get us started on it. So lightning is an amazing natural phenomenon. It happens both in the clouds, but it also happens, from your fingertips or the tip of your nose. If you've ever slid down the plastic slide at the playground and kind of gotten a zap when you hit the floor, or maybe you touched your pet dog or you touched your little brother and you got that zap, that is lightning. And it all has to do with the separation of electric charge. Matt very nicely gave us that foundation of what are electric charges. And they're balanced. So you are full of both positive and negative charge, as is the playground slide, as is typically the clouds in the sky, equal numbers of positive and negative. When inside a cloud, things start moving around, the water droplets, the ice crystals, the dust particles, as they move past one another, those charges get separated, much like if you've ever taken a balloon, rubbed it on your head, and then your hair kind of stands up. Positive charges and negative charges will attract towards each other, same types, whether negatives or positives, those will repel or push away from each other. So when you get that separation of charge inside of a thundercloud, what's going to happen is those negative charges that collect at the base of the cloud are going to be attracted towards the ground. As they move towards the ground and meet those positive charges, bam, that's when we get the lightning bolt. And what's happening is we are superheating the air. That's what makes it glow. That's what makes that snapping sound that we might call thunder. And that's also what produces the immense heat. So if that lightning bolt strikes something, say like a tree or a house, it could possibly start a fire. It's not all that common that houses get struck by lightning on any sort of regularity, so don't be worried about that. Yeah, so that's what lightning is. That's how it's formed. With their third part, Christina?
Sorry, I'm looking at other questions as I'm also thinking about the one I just asked. They wanted to know, how does it work? How is it made? And what is it?
I think I mostly covered all those with my long explanation.
Excellent. So then we will go on to our next question. This is from Isora, 9 years old, who would like to know, what will happen if lightning hits you?
I can start with that. You might remember that one of the things I mentioned that I liked about electricity is the fact that it's even contained in us. Living things use electric currents to time how the heart beats. When your brain thinks and when your nervous system works, that's transmission of electrical currents via charges changing place. So one of the problems with a lightning bolt hitting a person is that it can scramble these systems. Now, the good news is not many people are actually killed by lightning. In the United States, it's the last few years, it's been about 20 people a year. And this is partly because it's fairly rare to get hit by lightning, and partly because in many cases, the cause of death is by your heart stopping from that overload. And if somebody's nearby who can do CPR, they can actually resuscitate you. So that is one of the dangers, is that the lightning can damage your nervous system or stop your heart. Another issue is that it can cause dreadful burns. As Karen mentioned, there's a lot of energy in a lightning bolt that gets turned to heat. So sometimes people do suffer terrible burns from a lightning bolt traveling not only over their skin, but even burns inside their body. So there's usually the worst things that happen when people are hit by lightning.
Not on my to-do list anytime soon, based on that description. But our next question, I think, is fun just because of my love of astronomy. Ben, 4 years old, would like to know, is there lightning on other planets?
That's a great question. And the answer is most definitely yes. So when we're talking about lightning here on Earth, it's those electric charges moving through our atmosphere or our air. Now, air is a whole mixture of gases. It's mostly nitrogen, a decent amount of oxygen, which is what we need to breathe, carbon dioxide, a couple of other trace gases. Other planets, namely the gas giant planets like Jupiter and Saturn, they have a lot of different types of gases, but electric charge is getting separated out and can as easily move through those gases. They might actually glow a different color, which is exciting to think about. And there are some great examples of different, well, let's call them space cameras. So different missions to these planets that have captured some of the flashes on other planets themselves. So yes, there is definitely lightning on other planets. You do need to have that gas. So something like Mars, a really close neighbor, similar in some ways to Earth, has a very, very thin atmosphere, and it doesn't readily have lightning bolts. I do think there have been examples of lightning bolts on Mars during dust storms. And that's, again, more caused by the dust getting whipped up by the winds, separating the charges, and then that discharge of a lightning bolt. But that's more about the dust storm and not just the natural atmosphere of Mars.
And I heard you mention about lightning colors, which I think is a good segue to another question here from Josue, who would like to know, why does lightning have different colors?
That's a great question that I can maybe get us started with too. So, like Karen was mentioning, those colors could be different on different planets, just really depending on the types of gases that are in that atmosphere. And that is really what's deciding what color lightning can be. So, if you've ever been to the Museum of Science and you've been in our Theater of Electricity and you had the chance to see one of our lightning shows, you might have seen that our lightning tends to be a sort of whitish, bluish color. And that's because our air here, and probably where you are too, is about 70% nitrogen, and a little bit of CO2, a little bit of oxygen, a little bit of other materials, but a lot of nitrogen. And so when those electric charges move through that air, it's going to give off this whitish bluish color. But if it moves through another gas, it could potentially give off another color. I know Karen has a couple of good examples there.
I always love talking about, so lightning is just electric current, charges moving through something, in this case, the air. But if you move that electric current through very specific gases, like neon, it's going to glow a particular color. So if you've ever heard of neon lamps or neon signs, it glows this nice bright red color because historically, at least, the signs were glass tubes filled with neon, run the electric current through them, it glows red. In other cases of similar gases to neon, like argon and xenon, you get blue and green, respectively, with those types of gases when the electricity runs through it. Just one thing that maybe you've experienced when you're watching a lightning storm from the window of your house or from your car, you might see almost natural lightning being a yellowish color. That's much more likely that it's being filtered by the clouds. So it's not necessarily the bolt itself is yellow. It's probably still a blue or a purple or a whitish bolt as it moves through our air, but it's getting filtered by the clouds around it.
And one quick thing I'll add is that we sometimes experience phenomena of lightning on Earth that has remarkable color. I'm going to share a picture taken from the International Space Station of Earth at night. And this glow you can see over here, where I'm circling the cursor, is a place where lightning is firing from clouds to the Earth. And you might barely see that there's some red wisps above it. I'm going to zoom in a bit so you can see those red wisps a little bit more. These are called red sprites, and they're a phenomena that often happens above thunderclouds, far above thunderclouds, as you can see. And I have to admit, I don't know a great deal about them, but another thing that does affect the color of light you get with gases is the pressure that the gas is at. You can have the same gas, and if it's at high pressure or low pressure, you do get different colors of light from it. So that might be one of the phenomena that causes those amazing red effects above a lightning storm.
You also sometimes get red lightning in volcanic eruptions, again, because of the gases that the volcano is spewing out, the particles moving around, producing the separation of charge, making an electric spark, but it happens to be that slightly different color because of the gases from the volcano.
This is all very cool. I think I want to look up more images of lightning colors later after this show. And for our next question, we have Emily from the Waterford School who would like to know, how does lightning transfer its energy?
I can get that started. Or Megan, I couldn't tell if you were starting to, okay. There's one of the big things has to do with a concept called resistance, which simply means, is it easy or difficult for an electric current to go through something? Now, lightning is funny in a lot of ways. When you get the massive flow of current that we think of as a lightning bolt, which is a part of what we call the return stroke, it's actually causing the resistance of the air, which is normally very high, to suddenly drop a lot. In fact, it becomes highly conductive, which means current flows well through it. However, it's still a massive amount of energy, so much that even though the air is conductive, basically the remaining resistance of the air will turn some of that electric energy into other kinds. So that resistance is a big part of why some of the energy will change to light as the atoms that make up the air and the electrons on those atoms get excited and they start to move. Some of that energy will turn into heat. And again, that's caused by these atoms being so excited that they move more vigorously, which is really one of the definitions of heat energy. And as those atoms move more vigorously, they slam into adjacent atoms and shove them and create what's called a pressure wave that eventually bonks you on the ear, so you hear a sound. So an awful lot of these effects are based on resistance. However, there are also magnetic effects that that convert some of the energy. Anytime an electric current is flowing, some of its energy becomes a magnetic field around it, and that can cause other kinds of effects that we don't typically experience with our senses.
Excellent. Thank you, Matt, for helping to clarify that. And for our next, I actually have two questions that I think are related to one another. So I'm going to pitch them both at you at the same time. So Carter, age 8, wants to know if lightning comes from moist clouds. But on the other side, Elizabeth wanted to know, can there be lightning that doesn't come from rain, like dry lightning, or does it have to be raining to have lightning? So you could kind of bring those two together to help us understand that concept better.
Yeah, both great questions. And often we hear about things called heat lightning because people will see it out across the open plains or meadows, and they look out and they see lightning in the distance, but they don't hear the thunder because it's too far away, and they don't have rain falling down. So they say, oh, clearly it's dry lightning. Now, you might get lightning strike before the storm really starts to drop a lot of rain. I don't know that there are many thunderclouds that can produce that motion inside to get the separation of charge and not be heavy enough with water to actually create rain. So yes, to the first question, it is definitely a moist cloud. Usually there are these long or tall towering clouds, has a lot of ice crystals and water droplets in it to get that separation of charge. And typically that does also come with rain. Matt, Megan, anything to add to that?
Megan? Yeah, Karen nailed it. Really, the thing about water on our planet is just we have a lot of it. It's something that's easily moved around by convection in the atmosphere, moving warm air and cool air, and that gets those rubbing effects going that start to transfer the charge in the first place. So that's why clouds are typically such a critical part of lightning on our planet. But as Karen mentioned, you can have lightning in thunders and in volcanoes where there's different kinds of things transferring charge. So yeah, we generally need the clouds to make the lightning.
Little lightning bolts when you touch the doorknob. You don't need a cloud, that's just you.
Well, I'm glad that we have the clarification of how water is involved in the lightning making process. On the flip side, Poppy was wanting to know if lightning is made up of fire at all.
As far as I know, no. It's really the light that you're seeing is just that heat of those electric charges pushing through the air. It can cause fire though. So I believe Matt was mentioning this earlier, or even Karen was mentioning this earlier, when a lightning bolt strikes, say it strikes a house or maybe a tree, sometimes it can result in a fire, especially if that material is really dry, which is something sort of relevant to a lot of the fires out on the West Coast, is that the materials are really dry. Oh, that's a great picture of, so that tree seemingly got struck by lightning and you can see it sort of exploded into a lot of different pieces, and maybe there was a little bit of a fire that resulted from that. But like I was mentioning, on the West Coast, things have been really dry lately because there hasn't been a lot of rain. And when a lightning storm may come around, it could strike some really dry material and set off a fire that way.
Not have enough rain to then put out that fire.
Exactly.
No, it's definitely a good thing to connect to current events right now. For our next question, it looks like Quill, age 5, would like to know, what happens if two lightning bolts cross one another?
Good question. It's a question we've gotten before. And two lightning bolts won't really cross each other because they'll either merge into one, or the way the charges are moving through that channel, like Matt was talking about, the channel of air, it's not two become one, it's really just one lightning bolt. And Matt, you might have a better explanation because I know you've
No, that's perfect. There's not electrically much reason for lightning to sort of cross each other like that. Sometimes it really can look like it. I've got one more picture which I think could sort of illustrate this. This is a photograph of lightning during a lightning storm. It's what's called a time-lapse picture, which means this didn't all happen at once. And this really bright one is the part we typically see during lightning, what's called the return stroke. All these little fiddly bits you see are called leaders. Those are places that are kind of like the first step of a lightning bolt, where charge is trickling down from a cloud and it sort of saturates the air. And sometimes it can fork off in different directions. Generally speaking, one of these leaders will contact close to the ground, and then all of this charge will sort of get sucked down that same path. But you can see over here, there's this kind of funny leader that looks like it's almost done a loop-de-loop. So sometimes it can look like it's kind of crossing over itself. It's still finding some strange path that it needs to follow based on the resistance of the air. But yeah, I can't think of electrically any reason why two lightning bolts would actually cross the same space together.
So I guess all of my drawings as a child were not scientifically accurate. And moving on to our next question, Sarah, age 8, would like to know, how fast is lightning?
Very, very fast, quicker than the blink of an eye. So light, especially, it's, move at the speed of light, the fastest thing that we know. I don't know. Do you guys have an exact metric for how fast it is?
I used to know this.
All I can think of is that like the flash that you see and you hear happens in about a billionth of a second. So because I actually have a video that's taken with a really, really high speed camera. See if I can get it playing here for you guys. And you can see this is 4.17 milliseconds per second. It's like an incredibly small amount of time. And you can see the counter down here. These are in seconds. So these are like thousandth of a second. And this isn't even what you'd be seeing yet. You'll get to that point where we get that, like Matt was talking about in his picture, the really, really bright one. So it does not happen in an amount of time that your eyes can actually see it and understand it. So that's pretty much what we would see, where you see that flash. And this is all less than, 4 milliseconds. So it is incredibly fast. Those charges, once the right conditions build up, it happens very, very fast. I don't have an exact like miles per hour or meters per second or anything like that.
Yeah, there's the NOAA has NOAA.gov has a great website with information about lightning. And I remember for our friend, if you want to look at the speeds, they have the data there about not only the speed of the return stroke, which is ridiculously fast, and the speed of those leaders I mentioned, which are significantly slower. It's a fun site. It's got some great info.
Thank you for that resource, Matt. And we have a question from Brady today, who wanted to know, how dangerous is lightning? But I might even add, if you could say anything about lightning safety on the flip side of that.
Sure. Lightning can be incredibly dangerous to a human or even to a tree. I mean, you saw that exploded picture that Matt showed us. So because we want to avoid being struck by lightning for many of the reasons Matt mentioned, the burns, the interruption of your regular electrical pathways, telling your brain telling your heart to pump and your lungs to work and all that stuff. So we want to avoid it at all costs. And there's lots of ways that you can keep yourself safe, but still enjoy a really great lightning storm. Number one is, if you have the option, be inside. When you're inside a building, even if that building were to get struck by lightning, those electric charges are most likely to move through the metal pipes and the metal wires. So it could cause fires. Unlike, again, houses aren't regularly struck by lightning. If you don't have that option, if you're outside, I'm going to share my screen again real quick. If you're outside and you start seeing this happen, nope, it still wants to be on the video. Hold on. If you start seeing this happening, that means the separation of charges is starting to begin. So these women, what they may not have known is just what a dangerous position they were in. If you can get to a car, a bus, a train, an airplane, a metal trash can, something where you were surrounded top, sides, and bottom by metal, if that object can get struck by lightning, those charges are going to move only along the outer skin. So this is actually something that we show off in our Theater of Electricity. So here you can see our nice metal bird cage. This is our presenter, Katie. She is getting struck by lightning, but she herself is not. She is safely inside of that metal enclosure. We use this to talk about why you're safe in your car. But if you don't have a house or a building of some sort, you don't have a vehicle or even a metal trash can, last but not least, the best thing you can do is be as low to the ground as possible with as little of your body touching the ground. You can see here, Leon's feet are touching the ground, but his feet are touching each other. He's crouched way down. So if lightning were to strike nearby, it would only go through his feet, not his whole body. If he were to lie flat on his back or flat on his belly, thinking, oh, I'm the lowest thing around, if lightning strikes the ground nearby, that electric current could move right across his heart. And that's really what we're trying to avoid when we are protecting ourselves from lightning bolts. That's the best way to protect yourself. And yes, it is dangerous.
Thank you. Those are all really great tips, Karen, to keep in mind if we're ever put in that predicament. And we have a question here from Lucy, who would like to know, really wants to know, why is lightning so bright?
Just a lot of energy, Lucy. That's a great question, but it's again, it's just one of those things that really emphasizes how drastically, first of all, the pathway it takes is often miles long. So if you think about the difference between a little tiny light bulb that you might have in your flashlight, that's got a filament that long, as opposed to like a big light bulb you might have in your house lamp. I'm dating myself a bit here because we don't really use these anymore, but it has a longer filament. Lightning is basically using a filament that's, several miles of atmosphere. So there's just a lot more stuff to make light in the first place. And then it's just a huge amount of energy that's got to instantaneously turn to other kinds. So I hope that's not too evasive an answer, but really it's just one of those things that just indicates how much power there is in a lightning bolt, that it can make up that much light.
Really that matter of scale. Your tiny lightning bolt, that goes from your finger to the doorknob versus miles and miles. There's just a lot of air that is glowing.
Awesome, thank you. And just looking at the time here, I think we might have time for one more question. So I'm gonna combine two together to just squeeze one more in. They are related to each other. And that is, Emily wants to know, can lightning move through water? And on a related note, someone asked, are you more likely to get hit by lightning when you're wet?
I think the first part of that question is, can lightning move through water, or can electricity move through water? And the answer to that is yes. So an electric charge can certainly pass through water. Water is a good conductor, meaning that it's a material that allows electric charges to pass through it really easily. So you do not want to be in water when a lightning storm rolls around. So you don't want to be swimming. You don't want to be on a boat out on the water. You again want to kind of find that shelter with multiple sides and a top to it. But I don't know about so much if you're just wet with water. I'm not sure that would have an actual impact. But Matt, Karen, what do you think?
Well, I was going to say, I'll add to Megan's before we get off the topic. Water itself is a really good insulator. The water we come across in our day-to-day lives has stuff dissolved in it, like salts and minerals, maybe chlorine or fluoride. It actually makes it, as Megan says, a very good conductor of electric current. And I think Matt was just saying maybe a teensy bit more likely.
Yeah, it's kind of related to one of those questions we get constantly about, okay, well, should I hold my metal phone while, or something small and metal, does that make it worse? Tiny bit. I mean, it makes you a slightly more conductive path. I wouldn't think that a situation like that would typically make you that much better of a target. At least I don't think there's any documented. Yeah.
If they wear rubber-soled shoes, they are safe from lightning. That is also not true because it's such a small amount.
Yeah, I'd say really it's exposure that's more the issue. For example, of the people that are killed by lightning, a lot of them are based on things like fishing, boating, and being at the beach. And I don't know how much of that is, that it's because they're wetter. It's probably, or that they're holding up a fishing rod. It's just probably that they're more exposed and have a harder time getting back to shelter than you typically would. So I wouldn't worry too much about being wet, but I would still try to get shelter as soon as possible in any situation.
Awesome. Well, thank you to our educators for giving such wonderful answers to all of our questions today. I'll have you all kind of say goodbye.
Thanks, everybody. Have a good day.
And I want to thank everyone who joined us today for being a part of the program. I'm sorry if you asked a question and you didn't have a chance to hear the answer to it. We had a lot of questions coming in today, but we're so thankful for your questions and for tuning in. Today, if you would like to learn more about other shows we're going to be offering throughout the week, you can check out our schedule by visiting mos.org/mosathome. And if you'd like to learn about how you can help to support the Museum of Science, you can visit our website at engage.mos.org/welcome to learn more about that. But thank you so much for joining our show. We hope to see you at the next one. Have a good day, everyone.